things to be aware of as using these multi-level models, some warnings, so to speak, would be to, of course, be very aware of the level at which these variables are being estimated. So be very conscious of whether the variables are being estimated at level 1 or they're being estimated at level 2. Another important thing is to always test that interclass correlation coefficient. Want to make sure that there is indeed enough variation at level 2 to justify these multi-level models. Due to the computational complexity of these models, there's really no need to use them if you don't have to. And likewise, always be aware of what your n's, or the number of observations you have, are at each level and the degrees of freedom that you're allowed. We don't want to overestimate our models, and we don't want to include too many things in a model with too few observations. In this case, we may have unreliable estimation, and we may not be able to have our models converge at all. Just some things to be aware of as you're moving forward in multi-level modeling. The most common problem in multi-level modeling is trying to include too many variables at level 2. Because of the nature of the data, it's very difficult often to sample many schools, or to sample many doctors, or to sample many countries, that we often have a smaller n at level 2 than we'd like, and we also often have a lot of predictors that we'd like to include at level 2. And so if we're thinking about doctors, for example, and we only have a sample of 50 doctors, which is actually quite a large sample if they all have 10 patients or so, we just can't forget that that level 1 n is not our level 2 n. And so we have 50 doctors. We may be interested in whether they're a specialist or not. We may think that that's an important predictor of their patients' outcomes. But we may also think that their experience is useful, so the number of years since they exited medical school. We may think that their gender is important. We may think where they practice is important. We may think that something about their practice is important. It's like the composition of their practice, the number, like the percent of women in their practice, or something like that might be important. But at that point, we've got 5 variables at level 2 with an n of 50, and so we want to be cautious in including too many variables at level 2. This is a pretty common problem. Another common problem is the likelihood ratio test that will tell you whether you should use a random slope or a random intercept model is rather conservative, and so you may want to think more carefully about, even if there are differences in the slopes, if they're sufficiently different. So we just want to be sure that they're subjectively different. If there's very little difference, even if the likelihood ratio model tells us that we should do it, we may want to reconsider, especially if we have a low n at level 2. For example, if we have 17 countries and we're interested in how being an immigrant varies across these countries, we may find that there are considerable differences in the slope of being an immigrant in these different countries. However, the actual effect may be very, very small. And if we have a low number of countries, it may not be worth it. We may just be better off sticking with the random intercept model. So you can use multi-level models without any level 2 variables. These would still account for the clustering within countries, although it's less common. Typically, multi-level models are used when we're primarily interested in how level 2 effects affect level 1 outcomes. So in this case, if we're looking across schools, we're most interested in how school funding affects student outcomes, taking into account that student SES is also likely to have an effect. Yeah, so there was a lot of concern over the ecological fallacy, which is using level 2 predictors to determine level 1 outcomes. So some would argue that we can't say that government spending on families affects the division of housework within the household. And so in this way, we're saying that something that happens at the level 2 that is equal for everybody is going to have an effect on your level 1 decisions, outcomes, actions. And a lot of folks are really concerned with this, but we would argue that a multi-level model will account for this. because not only does it account for all the individual level factors that may determine whether you are doing your housework or not, or whether your husband is doing your housework or not, or what have you, is also, so that's accounted for, but we also, by having a sample of many countries, we can see how this varies across country as well. These multi-level models allow you to take into account both of those. In many ways, this has allowed us to examine ways in which group level factors affect individual level outcomes. While these models allow for us to control for a lot of the between country variation, we still, when we're only looking at a cross-section, we're still only providing descriptive analyses. So, which is to say, these are not causal, and so your language in writing up your results should reflect as such. Again, we've controlled for a lot of variation and adjusted the model so that the estimate should be as accurate as possible. To make a truly causal argument, we would need some sort of temporal data, and that would be multiple waves, for example, of data over time. Multi-level models are a useful tool when we're interested in how observations nested within groups are affected by both level 1 and level 2 outcomes. They're pretty easy to utilize, given the adequate data structure, and can give you a lot of useful descriptive information on how level 2 characteristics impact level 1 outcomes. Just be careful that you're using them adequately and safely.